In this video, we will cover graph basics. We will start with understanding graph representations. We will discuss key concepts such as what are graphs, their vertices and edges. We will explore the difference between directed and undirected graphs, as well as weighted and unweighted graphs. Finally, we will learn representation methods like Adjacency Matrix and Adjacency List with their trade-offs and applications. A graph is a nonlinear data structure that consists of vertices, also known as nodes, which are the points in the graph, and edges, which are the connections between the vertices. Mathematically, a graph G is an ordered pair G equals V, E, where V is a set of vertices and E is a set of edges connecting these vertices. Let's explore the different ways to classify graphs based on their properties. Graphs can be classified into directed versus undirected graphs. In an undirected graph, edges have no direction. On the other hand, in a directed graph, edges have a direction, indicating a one-way connection from one vertex to another. Another way to classify graphs is weighted versus unweighted. In an unweighted graph, all edges have equal importance. In a weighted graph, edges have associated weights or costs, representing different values for each connection. An adjacency matrix is a 2D array of size V by V, where V is the number of vertices in a graph. The value of matrix at position I, j is equal to 1 if there is an edge from vertex I to vertex j. Otherwise, it is 0. Let's discuss some key characteristics of adjacency matrices. They have a space complexity of order of V squared. Edge lookups are very fast, taking only order of 1 time. For undirected graphs, the matrix is symmetric. For weighted graphs, instead of storing one, we store the weight of the edge. Let's consider an example of an undirected graph with vertices A, B, C, and D. The adjacency matrix represents the connections between these vertices. A 1 indicates the presence of an edge, and a 0 indicates no edge. The highlighted values show the connections, for example, between A and between B and D. Let us see how to implement an adjacency matrix in Python. We define a class called graph. In the init method, we initialize the matrix with zeros. The V is the number of vertices. The graph is initialized to 2D array with all values 0. In the addEdge method, we add an edge from vertex U to vertex V by setting the value to weight. For undirected graphs, we can add an edge from V to U as well, making the matrix symmetric. The print matrix method iterates through each row in the graph and prints it. When initializing, create a V by V matrix filled with zeros. When adding edges for directed graphs, set matrix UV equals 1 or the weight. For undirected graphs, set both matrix UV and matrix VU. Remember that it requires order of V squared space, regardless of the number of edges. It is efficient for dense graphs where the number of edges is approximately equal to V squared. Checking if an edge exists takes order of 1 time. Finding all neighbors takes order of V time. An adjacency list represents a graph as an array of linked lists. Each index of the array represents a vertex, and each element in its linked list represents the vertices that form an edge with that vertex. Some key characteristics of adjacency lists include a space complexity of order of V plus E, where V is the number of vertices and E is the number of edges. Edge lookup takes order of the degree of the vertex. Adjacency lists are better suited for sparse graphs where the number of edges is much less than V squared. For weighted graphs, we store vertex weight pairs in the list. Let's consider an example of an undirected graph with vertices A, B, C, and D. The adjacency list shows the neighbors of each vertex. For example, A is connected to B and C, while B is connected to A and D. Now let us see how to implement an adjacency list in Python. We define a class called graph. In the init method, we initialize a list of lists. V is the number of vertices, and the graph is a list comprehension that creates an empty list for each vertex. In the addEdge method, we append the destination vertex V to the source vertex U's list. For undirected graphs, we also append U to V's list. The print adjacency list method iterates through each vertex and prints its corresponding list of neighbors. When initializing, create a list of empty lists for each vertex. When adding edges for directed graphs, append the destination to the sources list. For undirected graphs, append to both vertices lists. It requires order of v plus e space. It is efficient for sparse graphs where the number of edges is much less than v squared. Checking if an edge exists takes order of degree time. Finding all neighbors also takes order of degree time. Let's compare adjacency matrix and adjacency list representations. In terms of space complexity, adjacency matrix takes order of v squared, while adjacency list takes order of v plus e, making adjacency list better. Checking if an edge exists takes order of 1 in adjacency matrix, while it takes order of degree in adjacency list, making adjacency matrix better. Finding all neighbors takes order of v in adjacency matrix, while it takes order of degree in adjacency list, making adjacency list better. Adding a vertex takes order of v squared in adjacency matrix, while it takes order of 1 in adjacency list, making adjacency list better. Removing a vertex takes order of v squared in adjacency matrix, while it takes order of v plus e in adjacency list, making adjacency list better. Adjacency matrix is best used for dense graphs where the number of edges is approximately equal to v squared, while adjacency list is best used for sparse graphs where the number of edges is much less than v squared. Graphs have numerous real-world applications. Social networks can be represented as graphs where people are vertices and relationships, like friendships or follows, are edges. Adjacency lists are preferred due to the sparse nature of social connections. For example, Facebook's friend suggestions and LinkedIn's network analysis use graph representations. Navigation systems use graphs where locations are vertices and roads are edges with weights representing distance or time. Shortest path algorithms rely on efficient graph representations. For example, Google Maps and Uber's route optimization use graphs. Web crawling involves web pages as vertices and hyperlinks as directed edges. Crawlers use graph traversal algorithms to discover and index pages, which is used in search engine indexing and web analysis. Biological networks represent proteins or genes as vertices and interactions as edges. These are used to understand complex biological systems and disease mechanisms, such as protein-protein interaction networks and gene regulatory networks. Let's summarize what we have learned. Graphs consist of vertices, also known as nodes, and edges, also known as connections, that represent relationships between objects. Graphs can be directed or undirected, and weighted or unweighted, depending on the application requirements. Adjacency matrix uses a v by v2d array for representation, and is efficient for dense graphs and edge lookups, taking order of 1 time. Adjacency list uses an array of linked lists, and is space-efficient for sparse graphs with order of v plus e complexity. Now that you have a solid understanding of graph basics, you can explore further topics such as graph traversal, like breadth-first search and depth-first search, shortest path algorithms, and minimum spanning trees. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.